Thank you, Phil. All right. It's turtles all the way down, a journey into modularity. Now, when we're talking about modularity, you will often think about software systems and infrastructure. And that's definitely a big part of it. But today in this story, we will cover modularity in many different forms. So of course, yes, software, microservices, software classes are examples of modularity. But also the way we organize, like organizations into departments or teams, are examples of modularity as well. And physical systems, like your phone, consists of a screen and a battery and a camera. And all of those are components of the system as well. That's a form of modularity. And even though all of these systems are very different, the same principles of modularity apply to all of them. And that is what we will talk about today. But let's start at the beginning and ask, what is modularity? Well, the definition that I follow is it's the principle of breaking down a larger system into smaller, self-contained, and interchangeable parts. So let's look at these in turn. Smaller, of course, modularity only makes sense if the resulting modules are smaller than the original system. Self-contained, meaning that the modules that you identify should be as independent of the rest of the system as possible. And finally, interchangeable, which means that if you have a module and it has a certain function, you should be able to replace that with a different module providing the same function without affecting the rest of the system. So let's take a look at an example. Let's consider any large web shop, like the place where you buy your books or your electronics. You could look at this web shop as a single entity, as a single whole, but that actually makes it kind of difficult to talk about. Are we talking about the technology or the business processes or the finance or the people or the logistics or the stock of this web shop? By breaking this down into modules, we can already conceptually make it easier for us. So for example, if we use the business processes as the dimension for modularity, we now see the inventory, the logistics, the finance, and the orders processes. And each of these modules, if you separate it this way, are of course smaller than the original system. They are self-contained, so each of these modules do not have too much effect on the other modules. And they are interchangeable. So you could take the logistics process that you have and replace it with another entirely different logistics process without affecting the entire system. So modularity is the design principle of taking a large system and breaking it down into smaller parts. And why is this important? Well, there are two main reasons. The first one is reducing scope. Let's say we have a large system like a car. This is a complex system. It has many different components, like its doors, its wheel, its navigation system, its transmission, all of these different components. And it also has many features, like the capability to drive, to navigate somewhere. Maybe there's an emergency system, the airbag system, and so on. But if I just be talking about the car as a single entity, and I tell you there's a problem with the car, I'm not actually telling you that much, right? You don't know if I'm talking about a engine problem or a driving problem, a steering problem, or a problem with the navigation system. And likewise, if I tell you or I'd ask you to improve the car, you wouldn't know where to start because I'm not telling you what I actually want to have improved. Do I want you to make it faster, safer, more fuel efficient, or more user-friendly? But if we split this up into separate components and we talk about the engine or the navigation system, this becomes much easier. If I tell you there's a problem with the engine, you know, okay, I probably need a mechanic. If I ask you to improve the navigation system, you know, okay, I probably need a software engineer or a UX designer. So modularity allows us to reduce the scope of what we're talking about. And this reduces the cognitive load of ourselves and the people that we work with. And it also makes it easier to locate problems, because in larger systems, problems are generally focused on a single area, right? It's not the entire car that's broken, it's probably just one component. And the check engine light that you have on your dashboard of your car is a prime example of this, because if that light turns on, it actually tells the mechanic, hey, I need to look at the engine, that's where the problem is, and not some other system. There's many of these different error codes that help here as well. So the first benefit of modularity is reduced cognitive load, which allows us to focus on a single module while not caring about all of the other modules too much. But we can't ignore that in this system, all of these other modules are still there. So in our web shop example, we said there's a finance module and an orders module. But this orders module cannot function without actually interacting with the finance module. The important thing here, and an important concept in modularity, is that the orders module does not need to know about the inner workings of the finance module. So when you, as an engineer or an architect, are working on the orders module, you know all the internal details, all the intricacies of your orders module, and you also know that you can call the finance module to send an invoice, or maybe that you can have that there's a logistics module and that you can call the dispatch operation on that module. But you don't know how these systems perform their job, and you shouldn't know. So in effect, we have abstracted away the complex logistics process into this logistics abstraction. Now, the interesting thing here is that modularity and abstraction are actually two sides of the same coin, where modularity is the concept of breaking down a larger system into smaller components to make it easier to understand how the system works internally. And abstraction is the principle of bringing those components back together again into a single abstraction. And what's interesting here is whether you want to apply modularity or abstraction in your designs and in your system depends on your role towards the system. So if you're a mechanic and you're looking at a car, you want to know about all the modules. You want to know about the engine versus the navigation system. But if you're a driver of that car, you actually don't want to know all of these things. You just want to consider the car as a single system. I will take my car, I will get into my car, I will drive my car, I will navigate my car to whatever I want to do. And you're abstracting away all of the details that actually make up that car. So it's a matter of perspective, whether you want to look at the single modules, the components that make up a system, or the system as a whole. And this system, this concept of breaking down systems into smaller components and then assembling them again into larger abstractions or bigger systems brings us to the second benefit of modularity, which is the ability to develop multiple of these components in parallel. Right? So if you have the engine and the door and the steering wheel and the navigation system and so on, you can have multiple teams working separately in designing and manufacturing them, and then bringing them back into the single unit again. And of course, this increases the overall speed of development of the system. So in summary, why are modules important? They reduce the scope for a single person or team, and they allow for parallelism across larger organizations and larger systems. And this increases the flexibility and the maintainability and the scalability of the system as a whole. And I want to focus here on the first word, flexibility, for a little bit, because I think in this audience there's many software designers and many software engineers. And we always say, we don't know what the future will bring, right? We built the solution for what we know now, but the market might change, the economic situation might change, our customer requirements might change. There's many factors that influence what we're building and what we should prioritize. But this is actually true for all systems. Whether you have an organization or a car, you don't know how your environment will change. Let's take the car example. We built gasoline cars for 100 or 50 years. And then suddenly we thought everything's going to be electric, and we started building only electric cars. And then we found out that people can't actually afford them, and now we're building hybrids and small, efficient gasoline cars again. The context is constantly changing. And if we would treat all of these systems as single units, then adjusting to these changes is very difficult. Well, if you break them down into smaller components, you can reuse the doors and the steering wheel and the navigation system while only changing the engine system. That's where modularity shines. But it's not a free lunch, because otherwise we'd just be separating everything into ever more smaller and more granular systems all the time. Now there's actual cost to modularity as well. So let's talk about overhead and complexity. Let's say you're making a hammer. It consists of two components, a hammer and a hammer head. Maybe one person is making this hammer, and maybe you decide, I will split this up into two people making this hammer. But now these two people need to communicate, right? They need to agree on the size of the hammerhead, about the length of the handle, the material being used, and most importantly, the way they are connected together. Are we going to weld them together? Are we going to use a screw or a nail? How large will that gap be? And how will we make sure that it fits? And if all of this overhead actually costs more time than having one person making the hammer by itself, then adding modularity in this system actually doesn't add any benefit. It's not worth it. And you can discuss this in the context of trade-offs. So on this slide, on the x-axis, we have the number of modules, and on the left y-axis, we have complexity and overhead. So what you see here is if you add more modules into your system, into any system, it will increase the complexity and overhead. But adding more modules also improves the limiting factors of flexibility, maintainability, and scalability. And every system has some sort of sweet spot where these two effects are in an optimal balance. And it is our job as engineers, as architects, but also as leaders, to find this sweet spot in all of our systems. But I do hope that you hearing me talk about modularity has made you realize that modularity and abstraction are actually human requirements, right? Us humans can only handle so much complexity in our heads. Us humans can only have teams that are of a certain size before the communication overhead becomes too large and we cannot manage it anymore. So we use the concepts of modularity to break it down into smaller, independent groups to make sure that we can keep a grasp on it. But the interesting thing here is that technical systems don't have this requirement. Like, if you have an application which is 50,000 lines of code in a single file, any computer will just execute it just fine, right? They don't have any problem with this single file. It's us humans who cannot handle and maintain such a complex code base. So we apply principles like domain-driven design, microservices, onion architectures, and so on, to add this modularity into our system so that we humans can maintain it. But that being said, us humans are everywhere, and so the need for modularity is everywhere as well. So let's take another look at another example and say we have this big multinational organization with tens of thousands of employees. Of course, that's too difficult to manage as a single unit. So we split that up into regional divisions, still very large, so we split it up into national divisions. But even national divisions are too hard to manage as a single entity, so we split it up into departments. And one of those departments might be the IT department. We still split that up further into domains, and maybe one of those is the finance domain. But even the finance domain gets split up into applications, and one of those is the invoicing application, which we split up into services, and one of those is the PDF generation service, which we split up into classes, and one of those is the database class, which we split up into functions, and one of those is the get line items function. Right, so we apply this principle of modularity everywhere, on every layer, all the time. So now that we've talked about modularity and its purpose, we can talk about coupling. Earlier we said modules should be smaller, self-contained, and interchangeable. But you should note that isolated is not on this list. Nor should it be, and nor can it be. So let's go back to our example of the web shop. We talked about the orders module, and we said it still needs to work together with other modules, like in this example, the front end calls the orders module to place an order, and the orders module itself calls the dispatch operation in the logistics module to do that dispatch. The way these modules interact with each other, that is called coupling. How are these systems coupled together? And the word coupling in itself has no intrinsic value. It's just a definition of the fact that things are working together. But we also often talk about loose coupling, and that has value. We say loose coupling is better than tight coupling. Right? There's an opinion or knowledge, experience in there. So let's explore what loose coupling means. In this example, we talked about the front end being able to execute the place order command. Now maybe you're an engineer or an architect working on the orders module. You should be able to change the internal workings of this orders module entirely without affecting the front end or the logistics module, your upstream or your downstream consumers. If you achieve that, then you've achieved loose coupling. Yes, they're coupled, but the effects and the changes that you have in the orders module do not affect your consumers. Now, in this concept, we're also talking about interfaces. Interfaces is how systems are coupled. So how the front end communicates with the orders module and how the orders module communicates with the logistics module. And if you look at it this way, you can state that every module, again, whether it's technical or physical or organizational, has an interface and an implementation, conceptually. So the interface is how you interact with the system, and in the implementation is what the system actually does internally. We also say that the implementation is the complexity of the system. This is where the actual processes happen. So we can also say that the interface is actually hiding the complexity of the module, if it does it well. If it's surfacing all of the complexity, then you kind of have a leaky abstraction, a leaky interface. And if you watched the reInvent keynote by Werner Vogels last year in 2024, he was talking about the concept of simplexity. And it's this concept. It's having a simple interface that hides the complexity, but also accepting that that complexity will always still be there, that you cannot remove complexity, that you can only hide it or move it to a different place. Now, if we're looking at interfaces this way, then that might lead you to the conclusion to say, okay, but then this interface can never change. I have to design it once, I have to design it well, and once it's there and it's being used, it can never change again. So it has to be stable. And maybe this is a good way to think about it, or at least a good thing to keep in mind. But there's a different level to this, and that is the amount of control that you have over the consumers of that interface. So let me explain this again with a diagram. Here on the x-axis, we have the control of consumers. How much control do we have? And on the y-axis, we have the required stability. And the relationship is linear. So let's say you're building a public API. You published it, there's API documentation that's live, your consumers are using it, you don't know who are using it, maybe you don't even know how they are using it, but one thing is for sure, you have very little control over your consumers. You can't tell them, hey, stop using this API, or maybe you can, but you're not making any friends if you do so. If you're in this situation where you have very little control over your consumers, yes, your interface needs to be very stable. But on the other hand, a function in your application code also has an interface, the function signature, right? And all the consumers of that function probably live in your own application. So you have a lot of control over those consumers. In fact, it might be just a simple refactor in your IDE to change all of the consumers in one go. So you have a lot of control, which means that you can change this interface all of the time, like every minute, if you like. It's probably not very efficient, but you could. So in this case, you have a lot of control of your consumers, and you require very low stability of your interface. Now, one last concept that I want to introduce about modules is the relationship between the interface and the implementation, and what makes a good module. So, a good module has a simple interface, an interface that you don't need to provide a lot of data to, that doesn't need a lot of detail or complexity. And on the other hand, a good interface, or a good module, has a deep implementation, which means that it does a lot of work for you. It completes entire processes, it has complexity, maybe it reaches out to other systems for you. That's how it adds value into your system. So a good module, in an example, could be an invoicing API, where you only have to provide, I want to generate an invoice for this user and this period of time. And when you do that, the system starts working and retrieves all the details of this user, retrieves all the line items for this user, calculates the sales tax, generates a PDF, maybe updates some CRM system for you. It has a deep implementation. That would be a good module. On the other hand, the opposite would be a shallow module. So if we take the same invoicing API, but now in this API we have to provide all of the details about this user, where they live, all of the line items. We have to calculate the sales tax before and send it to the invoicing API. Maybe we have to specify what we want the PDF to look like. Then we have a very wide interface. And the system itself actually doesn't do that much. It just takes whatever you provide and does a single operation on it, maybe generate a PDF, and returns that. So it has a very shallow implementation. And this would be a worse implementation of this API. And this applies to all systems again. So you can remember, modules should have narrow interfaces and deep implementations, or to put it very shortly and simply, modules should be deep. And one very interesting area where you can apply this same idea is in human interfaces. So if you look at a team is considered a system. Like if you talk to any social scientist or behavioral scientist or organizational scientist, they will say, yes, a team is a system. And if a team is a system, then the people in it are its components, its modules, if you like. And the funny thing is that every person also has an interface. This is how we interact with each other. And we have implementations. If I ask you to do something, you start doing that work. That's your implementation. That's your complexity and your process. So if you look at it this way, you can apply the principle of broad or narrow interfaces and deep modules here as well. Let's say you have a colleague who just joined your company. They're very inexperienced, just out of school. You have to tell them everything that they need to know, or that they need to do, because they don't know it yet. They're very inexperienced, so they have a very wide interface. And then you tell them what to do, and they do exactly that and nothing more. So they have a very shallow implementation. This is not a judgment, this is just because they're inexperienced. That's something that they need to grow in as well. So as they grow, and as they get more experience, maybe at some point you don't have to tell them all the details of what they need to do anymore. You just tell them, hey, this is the solution, go find out how to implement it. So you're narrowing the interface, and they are deepening their implementation. Then again, if they're getting more experienced, you don't tell them what the solution is anymore, you just give them the problem. And they go find out different solutions, their trade-offs, make the right selection there, maybe discuss it with their colleagues. So again, we're narrowing the interface, and they are deepening their implementation. And maybe they get at some point very experienced, and you don't even tell them what the problem is anymore. You just give them a goal. Say, hey, I want to achieve this goal. And they go find out all the problems and all the different solutions and all the complexity of that. So we have the narrowest interface and the deepest implementation. Now, in the last section of this talk, I want to move it a little bit out of the conceptual and into the practical, and share how we applied this concept of modularity at PostNL, where I work. In PostNL, we have about 30,000 employees, so it's definitely a big organization. Definitely too big to manage as a single entity. So what we did is we split it up into business units. Of course, very common practice. We have e-commerce, mail, digital, cross-border solutions, and some others. And then within each of these business units, we have an IT application landscape. But we made a mistake here. We have all of these applications that have their own specific functionality, and we allowed all of these applications to communicate directly with each other. So now we have this mesh of applications all integrating with each other, and that is leading to tight coupling. Because if one of these applications has an interface, then all of these applications are dependent on that interface. And remember, if you don't control your consumers, your interface has to be very stable. So now the team maintaining this application comes into a situation where they can't actually easily change things in their system, because there's so many systems dependent on it. And also, we've seen that many of these applications actually belong together because they perform some sort of a single business function, like maybe orchestration or distribution or sorting in our systems. And we've seen that they belong together. Maybe we even have our leadership together in a single area like this, but the applications are still separate. And as an effect, on the left side of this diagram, you have all these applications who now need to know about the internal complexity of this domain to understand how they can achieve their goals. Which applications do they need to? Which one of those perform that specific sub-function that they're looking for? So to solve this, we're introducing domain boundaries, domain interfaces. And this is where we decouple the left side of the application, the consumers, or of the landscape, the consumers of this domain, from the right side, which is the internal complexity of the domain. And this is, of course, well, the interface and the implementation. And as a result, the left side now no longer needs to know about the internal workings and the internal details of this domain. And on the right side, the developers get a lot more flexibility to change their landscape the way they see fit, because they are decoupled from their consumers. And the long-term goal that we have at PostNL that we're working on now is to separate all of our business units into these functional domains and give every one of them a stable interface, which would make our IT landscape much more flexible, much more scalable. So I hope that you've seen that by applying the principles of modularity, we can improve the flexibility, the maintainability, and the stability of the system. Sorry, the scalability, also stability, but it's not on the slide. But you should also realize that by adding more modules, you're also increasing the complexity and the overhead in the system. And if that overhead becomes too much and the complexity becomes too high, we can then again use the principle of abstraction to bring things together again and add this abstraction layer into our systems. And this results into decoupling our landscape, more flexibility within the module itself, and information hiding for all the different consumers. And that leads us to the conclusion, which is that whether you separate a business into domains, or an application into microservices, or a code base into different concerns, or a physical device into different physical components, modularity will help you build evolvable systems at any scale. But to make sure that this modularity works, you have to make sure that the modules you create are actually smaller, self-contained, and interchangeable. If you don't do this, modularity will not actually help you. And remember, nothing comes for free, so every level of granularity that you add into your system will add a little or a lot of complexity into your organization as a whole. And balancing these trade-offs, I think, is one of the most challenging, but also one of the most fun parts of our jobs. I hope you think so too. So I hope that this session has provided you some new insights into modularity and abstraction, and I hope you will enjoy the rest of Community Summit today. Thank you.
Fabulous. Thank you very much, Luc. Are you open to questions?
I am open to questions.
Okay. This is going to be a workout, isn't it? Who's got a question for Luc? Who's got a question for Luc? Ah. No? No hands up.
No questions.
No questions.
I must have been very clear. Also, I can't see anyone with the light.
No, you won't be able to. Yes, we have one, I can see. Sorry, guys.
Hi, it's a very interesting presentation, Luc. Thank you so much. It's Keith Roberts from Logicata. So, talking about the stability of the interface, I mean, a lot of this reminded me about object-oriented programming. So, if your developers want to change, say, the name of one of the function calls in the interface, okay, one of the messages, how would you go about it? Would the best way to be, say, we're deprecating this function call, part of the interface, we're deprecating the name of that one, and then you create a new name for that function call, if you're with me. So you don't just scrap or write off the one that the developer's currently using, but you say, this is deprecated, but we'd like you to use this new name. Would that be a viable way, practical way of doing that? Please?
Yeah, the speakers are facing that way, so it's a bit hard for me to make out what you, the question. But if I understand you correctly, saying if you have an interface and you have a certain stability and you have consumers of that interface and you still need to make changes, how do you go about that? And deprecation is, I think, the example that you used. Yes, deprecation is absolutely a valid approach there. So in this spectrum of requiring a very stable interface from having a very dynamic interface that doesn't need to be stable at all, it is a spectrum. So somewhere in the middle, you might have a application library that you publish to your users, and maybe you can reach out to those users because you know who they are if it's an internal library. You still need to be, I think, you still need to, what's the word, hold back on trying to introduce too many changes, because this creates additional work or what's called change amplification into all of these teams. But if you really must, then yes, deprecation is a way to say we intend to not use this function anymore, and it will be gone, or not provide this function anymore, and it will be gone in 1 or 2 or 3 versions from now. So start migrating. And that's, I think, a very kind of midway solution where you balance the fact that you do still need to do that, but also want to reduce the impact on your users as much as you can. So yes, deprecation is definitely a valid approach there.
Okay, thanks
I hope
much.
I answered your question.
Thank you, Luc. Cheers.
Now we've got questions. So we are. I will take one question, and then if I could ask you to just catch up with Luc afterwards, just because break time is upon us.
Okay, at the beginning you mentioned the idea of the car and the different components, you know, the engine and the navigation system and so on. And then the idea of the
sorry,
user.
I need to interrupt you. I can't hear the question.
Oh, sorry.
Maybe you can
Make
speak
it louder, okay.
Yeah.
Okay, so the idea of the car at the beginning with the different systems, the engine and so on. And you mentioned the idea of the user saying that they had a problem, like they wanted the car to be more user-friendly or an improvement. How do you go from that kind of idea of those components that the user doesn't really care about to their kind of language? How do you kind of map between those two domains?
So if I understand the question correctly, it's how do you translate the composability of the systems and modularity of the system? How do you surface that to a user while they actually don't care, but need to propagate that to somebody who does care, like a mechanic? Is that correct?
Yeah, exactly.
Okay, thank you. Yeah, that's an interesting question. Do you know, like, if you have a car, it sometimes tells you stuff, or any computer system and an application, it sometimes tells you stuff that doesn't make any sense to you. Like, maybe you work on Windows and it crashes and it says error code 0x24b. Like, okay, I don't care. I think this is one of those examples, and with the car as well, if it just shows some sort of error code, where you're like, okay, I can't handle or deal with this information because I don't know how to actually process it, but it is the information that you need to provide to a system administrator or a software developer or a car mechanic who can take that information. And there's a balance. I think this is, in a way, is a leaky abstraction, because you're leaking the internal complexity of the system out to the user who doesn't care. The alternative is to not do that. Say, there's a problem with your car, go into the garage. Or there's a problem with your computer, go to your systems administrator. And that's also a valid option, but it kind of makes the user feel, I think, more impotent in a way. Like, okay, you're telling me something, but there's nothing I can do. So, but it's my system. Like you're like, out of control then. So I think there's actually a usability kind of balance there, where you have to choose how much information you do want to surface to take your user seriously, but also let them know you probably shouldn't fix this yourself unless you're actually a mechanic. So, difficult topic, and more of a usability than a technical question, I think.
Yeah, thanks very much.
Lovely. And I am sorry, do go and chat to Luc directly. You going to go and have some coffees and pastry, Luc?
I will be here all day. I will be here at the stage for a few more minutes.
Awesome. Thank you. And once again, round of applause for Luc, please.